Good evening, all of you. Thank you for joining us in this webinar. I can see 17 already have joined the session. I have with me Dr. Jacob Wickham, who will be our trainer for today. My name is Daniel, and I am from Cactus Editage, and I oversee the partnership with King South University. Thank you so much for making time and for joining this session titled Everything You've Always Wanted to Know About Statistics. And this is one of the first, kind of a webinar that we're doing with King South on a topic that we believe, has been requested and is much required by the researchers at King South. And we hope that as Dr. Jacob brings this, topic and this training to us, that it will benefit you. As usual, we would love to hear your feedback on this topic, your suggestions, and how you would like us to prepare for future webinars. Any topics that you would have in mind, or just extensions of this same topic that you would like us to cover in future webinars. Then please do that. At the end of the webinar, there will be a feedback form that we'd love for all of you to fill in. Also, please let your colleagues know that Editage continues to do these webinars once every quarter at least, and I believe we'll do at least one more in next month, in March. And so we'd love to hear your thoughts on what you would like the topic of that webinar to be. As always, I just want to thank the investigators support unit at King Saud University, associated with Prince Knife Research Center. I want to thank Dr. Niazi for facilitating this partnership and for allowing us to bring this webinar to you, to the good people at the investigators ISU unit, and for their support in helping us to just arrange this and to bring this webinar to you. If you have any questions, feel free to write into investigators support unit. The email address should be there with you, or you can always check with your department. I will also put in the email address in the chat window. So if you have any questions, any requirement for service, then you can always get in touch with them. Editage, of course, provides statistical analysis services to King South University researchers. So if there are needs that you have, you can always bring them to Editage, and we would love to help you with your requirements. Again, you need to just get in touch with the ISU unit to uh, see about that. Okay. With that, I'll hand over to Dr. Jacob Wickham for this webinar. Comes with many years of experience as a researcher, as a faculty member, as a journal editor, and so bringing all of that expertise to bear, and talking to us today about statistical analysis, and what all researchers should know in terms of just where to start and how to go from there. Okay, so thank you, and have a good time. Dr. Jacob.
All right, thanks, Daniel, for the introduction. My name is Dr. Jacob Wickham. I'm tuning in from Moscow, from Russia. I've been here for slightly over a year. I spent most of my time academically in Asia, actually in China and the U.S. So I'm going to share my screen, and I've been a journal editor for 9 years now, and it's very important that the statistics are done properly, and usually we ask reviewers to comment on the statistics, and they'll give some feedback on it. And of course, with any study, that you should provide enough information about how the data were collected, how the data were analyzed, and of course present the data in a meaningful way in your paper. But before you get into that, it's good to have a fundamental understanding of statistics. And so I'm going to share my screen right now. Can everybody see my screen? Okay, it looks like yes. So thanks again, everyone, for joining us from King Saud University, Medical City. And I've been with Editage for over 5 years now as a trainer, and my part-time job is a I'm an editor for a multidisciplinary journal, Integrative Zoology. This is a society journal, the International Society of Zoological Sciences, and our publishing partner is Wiley. We're a Q1 journal for the last 5 years. So here's a brief snapshot of editage, and I gotta mute my phone, apologize. And Uh, Editage, a big bulk of their work is on helping to edit papers and help you get your papers in good shape for publication. They also have a branch of training, which these workshops are a part of. They've helped over 500,000 researchers publish over 2 million papers, and they now have over 20 years of experience. So this webinar is part of their educational branch. And then here's a little bit about me. Here's a couple cover photos from the journal where I've worked at since 2014. And I finished my PhD in 2009 and did my postdoc in the Chinese Academy of Sciences, first at the Institute of Chemistry and then at the Institute of Zoology. I'm also an adjunct professor at Rutgers University in the United States. And I just started a new position uh, just over a year ago at the Severtsov Institute of Ecology and Evolution, Russian Academy of Sciences. I can talk to you today both from the perspective of a researcher and also from the perspective of a journal editor. And statistics, it's very, very important to have good statistics in your papers. And to give you a good foundation of statistics, that's the purpose of this webinar. Just give you an outline here. I'll go over the different types of data and understanding the different types of data, and then understanding and describing data distributions, and then the statistical procedures. There's statistical trends. Uh, you know, every paper reports statistical results, and uh, usually there's a choice of your statistic, whether it's a parametric test or a non-parametric test, and then it gives you a p-value. And we actually caution researchers to avoid overemphasizing p-values. Actually, there might be some differences that are not statistically different, but they might be biologically different. But of course, uh, you know, researchers want to attain that zero point zero 0.05 threshold, and there are statistical tests. But there's we've actually had some researchers over the years. They report like p-values 0.06, 0.07, and they say there might be a meaningful difference here, but it wasn't statistically different. And then we get into research questions and how to do hypothesis testing and various statistical analyses. Then I'll talk about accuracy and precision. You've probably all seen the graphics with the dartboard, explaining accuracy and precision. And then I didn't write. There should be a number 7 there, and I'm going to actually give you some resources on statistical language programming. You may have heard of the program R, and just as a journal editor, I'm finding more and more of the statistics that are done in scientific papers are done in the R platform, and it's becoming very, very important, not for just ecologists, but for medical researchers and every researcher to start learning R. And I got a great book to share with you that's written at a very elementary level, and this is a great way to start learning R on your own. So first off, what are statistics? Statistics are quantitative understanding of a phenomena. They're an analysis of data, and usually it's quantitative data. It has discrete values, and these are obtained via survey. Well, that's basically another word for sampling. So you obtain data from sampling. And there's different methods for understanding data, the distributions of data, and then what statistics tests that you should choose based on whether you have a normal distribution or a non-normal distribution of data. And then there's lots of methods to understand your data, and there's comparisons like means, the variances, standard deviations, standard errors, and of course you want to present the data. Like usually the highlight of any paper is the results section, where you can, this section is supposed to be dominated by figures and tables, and it'll give readers a chance to understand the distribution of your data. That's why it's, you know, you can use tables if exact values are more important than the overall trends, or you can use graphical representations if the overall trends are more important than the individual data values. And usually such data will have like a mean or a variance or a standard error or standard deviation. And you can use error bars or other ways to show the spread of the data. So the objective is to gain an understanding of data that contains variance, so that has some variability. And that's what the end goal for statistical analysis. So there's two functions of statistical analysis. One is it makes estimates about an entire population from a subsample of that population. Of course, you don't have unlimited money and unlimited resources. From any population, it's impossible to sample the entire population. So you have to make inferences from a partial data set, and that's a sample. And you can make estimations and inferences from that. And then secondly, to reveal the underlying structure of the data, and that's when the analysis comes in. And you can quantitatively summarize and classify data obtained from such a sample. If you have any statistics courses at your medical university, I encourage you to take them. When I was doing my graduate training, I took as many statistics classes as I possibly could. It wasn't until my PhD, my coursework for my PhD, where I think I took a majority of my statistics classes. So understanding types of data. There's nominal or categorical scale data, and these are basically measures data grouped into categories. And actually, I call these dummy variables. For example, male equals 1, female equals 2. Here, the size of the values has absolutely no meaning. You're just categorizing the different the measure of data. And these can be basically just a dummy variable. You just categorize. So here, calculating averages or totals is completely meaningless. So then the other type of scale is the ordinal scale. This measures data where numerous values show only the relative rank of what is being measured. So having the ordinal scale, there's actually some statistics tests, you've probably heard of them, like the Wilcoxon rank sum. And basically it ranks the data, and you're comparing two different data sets according to the ranks of the data. And ranking is just, one number is higher than the other, it has a higher rank. So here again, calculating averages or standard deviations is meaningless. But if you have a median value, the middle value, or a quartile deviation, are the data in the top quartile, middle quartile, upper middle, lower middle, or the bottom quartile. Here is where you can actually get some meaning from your data. So those are two scales that are used: nominal scale, the dummy variable the categories, or the ordinal scale, which is more of like a ranking system. So they both have their uses, but you can do different statistics tests based on whether your data is ranked or if you have real quantitative data. So here's a couple more scales I just wanted to touch upon. One is the interval scale. This measures data where the differences between the objects of measurement that you are measuring are meaningful and equal. So here are a couple examples here are temperatures or IQ. There's no absolute zero in that in IQs, but it is possible to calculate averages and totals. And then another scale is the ratio scale. This measures numerical data that can have a meaningful 0 point. So, I guess with temperature is probably the Kelvin scale, where you have absolute zero, but you don't have any negatives. So now getting to the ratio scale, here is numerical data that has a meaningful 0 point. So this can be length, weight, and then uh, I know you're in the have a medical university background, so it can also include blood pressure or grip strength. And here it's possible to calculate averages or totals. So here's just a note on the interval scale. There's no need to clearly distinguish between interval and ratio scales for statistical analysis. In reality, data are usually separated into quantitative categorical data. These are um, qualitative, sorry. The first one there is qualitative categorical data. Now, these are nominal or ordinal scales, like the rankings. Or you have quantitative continuous data, and these can be intervals or ratio scales. The data that you're used to collecting that have, um, you know, you can calculate means, averages, and standard deviations and variances. And that gets us to understanding and describing data distributions. So if you have a data sheet, if you typed all your data up into Excel or some statistical program, one way to look at your data, and this is part of the data exploration. Of course, you can do really fancy um, uh, analysis of the variance, or you can do linear regression or uh, multivariate statistical analyses. All these very complex analyses are fine, but it's also good to understand basic descriptive statistics of your data. And one way to look at that is looking at frequency distribution tables. This divides data into levels that show the frequency for each level. A table can separate a given variable into levels and records and records the number of data points at each level. So this is one way to look at data, simple descriptions of data. For example, you have testing scores here, between 50 and 100, and then just the number, the frequency in that range, and then the cumulative number of you know, it's actually starting from lowest to highest, the cumulative frequency, the number of people, and of course it includes everybody when you get up to that last category. And then you can have distribution ratios, relative frequency, and then the cumulative relative frequency. So you can make some simple histograms using that data table. And this shows the distribution of quantitative data as a frequency distribution. And then the cumulative ratio is this line graph that is superimposed on this bar graph. You can almost see that there's a standard bell curve for the testing scores here. So it makes it easy to understand data distributions visually. But just a word of caution here that this can give very different impressions according to the interval that you select for each level. You can look at smaller intervals or even larger intervals. And of course, the graphs will look different. So it's important to choose the appropriate interval. So here is an interval of 2, and this shows um, you know, much more precise distribution. And then there's an interval of 20, which I don't think contains very much useful information because I think most of the scores are clustered around 80. So, so there's just different ways of looking at the data. So there's common histogram shapes. There's a normal distribution. I mentioned the bell curve. You can have a bimodal distribution. This is where you have two peaks in the data. You can have a skewed distribution where it's skewed to the left or skewed to the right. I mean, these don't have to be scores per se. These can be other measurements. Maybe length or something, length of someone's arm. And then the last distribution here just shows an example of an outlier distribution. You have most of the data points are observed here, and then you have an outlier with a couple values. So here's some other types of graphs to show a data distribution. This is actually the impact factor of the journal where I work, and here I plotted on a bar using a bar graph um, the percentile of the journal's impact factor as it relates to other zoology journals. And then the impact factor is actually in blue here, superimposed on this graph. And so another type of graph is a box and whisker plot. And uh, this shows a quartile distribution. Uh, I think this is used a lot in the medical sciences. So um, the first quartile is a range of impact factors of journals in the top, Q1 journal, and you can actually see there's a very big distribution of impact factors, and then the Q2 and Q3 is the next 25%. So it's the 25 to 50%, and then the 50 to 75%, and then Q4 is the bottom 25%. And then the average is this line in the middle where it shows the between the second and third quartiles. Actually, that's not a mean. It's actually a median. Median is where half the values are above this point and half the values are below this point. So I just wanted to talk about mean and median. So to obtain the median, if you have an odd number of data points, it's the value of the middle data point. So here you have um, you know, 7 different values, and the middle rank is actually number 4. So your median will be 92. And if you have an even number of data points, so here's 6 data points, here the median will be 91.5. And if you calculated the average, um, I would say the first data point is an outlier. It's very low. So the overall average is very low. So here I think the median is probably a better description of both these data sets rather than the mean, the average. And plus minus, this is usually a standard error. So that's actually a very large standard error. So the median is normally used in the case of outliers or non-normal distributions, which of course this is non-normal because of this outlier as the first data point. Another way to visualize data is to do a scatter plot. Usually this is done before you calculate a linear regression. And you can plot the relationship between two variables. This would be a good one for medical sciences, just a scatter plot of height and weight, and you can try to fit a curve to these data or do a linear regression. And it's an easy way to understand data distributions and correlations. So there's a number of statistical tests that you can do on this. So you can do a linear regression or a nonlinear regression, depending on how you fit the data. So now getting into statistical procedures. So when you have a data set, one of the first things you want to do is just to see if the data follows the assumptions of having a normal distribution. So, this can be done. Sorry for the Japanese written on the bottom of the page here. But you can do a test for normality, and you can either use the Shapiro-Wilk test or a Levin's test. And these tests will be able to tell you if your data are normal or not. If they qualify as following a normal distribution, then you can use parametric statistics. However, if they fail this test and you have a non-normal distribution, then you'll be using non-parametric statistics like Kruskal-Wallis ANOVA compared to ANOVA, or a Wilcoxon rank sum, instead of doing a t-test. So there's normality tests, and then homoscedasticity. Homoscedasticity is the equal distribution of variances. And here you can do the Levine's test. I'm glad that's written there. So the Bartlett's test or Levine's test. There's also the F test. I would recommend the Levine's test. This one I've used on my dissertation research, and it's important to do a test before you start choosing parametric or non-parametric statistics. And basically, when you're comparing two data sets, there's an assumption that they came from the same population. So the distribution of the two data sets are equal. So, and here, on the graph on the left, they do have equal variances. Yes, the means are different, but the variances are equal. And on the second example, I know you cannot read Japanese, but I will translate. These are two populations that have probably from different populations. So it'd be very difficult to compare the means between, or the variances, do an analysis of the variance between these two data sets. So you have to use non-parametric statistics. And with any data set, you should be able to have a hypothesis that's established, and then your null hypothesis is used to judge whether a given hypothesis is correct or not. In most cases, a null hypothesis assumes that the given hypothesis is negated. So basically, your null hypothesis is there is no difference between the means of these two groups that I'm comparing. So that's your null hypothesis, is that there is no difference. And if you can reject your null hypothesis, then you accept the alternative hypothesis, meaning that there actually is a difference between the two data sets. And this is your alternate hypothesis. For example, a new method of muscle training is discovered in the medical sciences. Is it more effective than other methods? Well, your null hypothesis will be the new method has no effect. And then your alternate hypothesis will be the new method does have an effect. So basically, it's an opposite hypothesis to the null hypothesis. So another procedure that everybody should be thinking of is the mean significance level. The alpha level. This is your level of significance of correctly rejecting a null hypothesis that is not true. So this is a reference value for the probability of discarding the null hypothesis. And usually in biology, the alpha is set at 0.05. So basically, you have a 5% chance that you're wrong when you reject your null hypothesis. So, and that's considered very, I would say, conservative in biology, and this is the acceptable probability threshold where you can reject an incorrect null hypothesis, with good statistical power. So this must be set prior to conducting any statistical analysis. It's the probability of mistakenly rejecting the null hypothesis when it is true. Thus, it is known as the confidence level, or alpha. So, you can be wrong 5% of the time, but it's still acceptable. So, in natural science, it's usually set at 0.05, or sometimes it's set at 0.01. There's also one and two-tailed tests. One-tailed test, these results are used when a result that would lead to rejection of the null hypothesis is known in advance. So you may know that one value is greater than the other, so you're only testing on one side of that standard bell curve. This is the region in which the null hypothesis is rejected, either to the left or the right of a reference value. And this is a one-tailed test. And when if you cannot predict any of your results, then the region is set to both sides of this reference point, and this is a two-tailed test. So the fourth procedure, this is actually you're assessing the p-values. The p-value is the probability value. This is the probability that a particular statistic occurs under the null hypothesis. If the p-value is below the significant level set beforehand, then the null hypothesis is rejected and the alternate hypothesis is accepted. And if the p-value is greater than the significance level, so if the p-value is greater than 0.05, then you fail to reject the null hypothesis, or you say the null hypothesis is not rejected. And again, 0.05 is usually the cutoff point for rejecting or accepting or failing to reject your null hypothesis. And before I lose your interest, I wanted to touch really quickly on statistical error. And this is why we choose 0.05 for the significance level. The type 1 error is this is a mistake that's made when you reject the null hypothesis, but the null hypothesis is actually true. There is no difference in your data. So you're incorrectly rejecting the null hypothesis. So these are results that are deemed significant when in fact they are not. And then the type 2 error, this is when you reject the alternate hypothesis, and you're saying that there actually is not a difference, but there's actually a difference. You just didn't find it. You didn't detect it in your statistical analysis. So you're deeming the results non-significant when in fact they are significant. So a compromise between these type 1 and type 2 errors, this is why the p-value is set at 0.05. So what is the opposite of significant difference? There is a difference, or we cannot say there is a difference. So what is the opposite of significant difference? Actually, the opposite of significant difference is we cannot say there is a difference. There might be a difference, but we can't say it statistically. Why is this? Why is it written like this? Why is our understanding of statistics like this? Well, it's because we cannot accept the null hypothesis. We just cannot say that there is a difference. Maybe the sample sizes were not big enough. Maybe the two populations are different, but we just cannot detect that there is a difference. So actually, instead of saying accept the null hypothesis, usually in statistical terminology, you can say you fail to reject the null hypothesis. So I wanted to touch briefly on avoiding overemphasizing p-values. So here is a study that was done. I just wanted to share the results. These were published in Nature. And These are wrong interpretations of statistical tests and p-values. And then they analyzed almost 800 articles across 5 journals and found that around half of these papers mistakenly assumed non-significant means or no effect. So uh, they said there was no differences, but actually there was a significant difference. So that was type 1 error occurring in these papers. So actually over half of these papers were wrongly interpreted. And these are data taken, you can see the reference from these journals. So don't interpret findings based on solely if the data are significant or non-significant. You got to take other factors into consideration. And there's a couple references that you can go and explore more about this example on your own. So I explained that there's a p-value of 0.05. And basically that means out of 100 times, that 5 out of 100 times you got the result by chance alone. And then 95 out of 100 times you got these results did not occur by chance alone. So when you're actually sampling from this population, you're hoping you're not going to sample those. Your study is not one of these 5. These are results that occurred by chance alone. And that means like there's significant differences that you discovered, but they were just you discovered them by chance alone. There really wasn't a difference. So what if your study is one of these yellow circles? If you just randomly selected one of these circles, and your entire study was is a yellow circle. So you may conclude there is a significant difference, even if there is not a significant difference. And this happens 5 out of 100 times. So that's where you get your alpha at 0.05, which alpha is 5%. And that's a matter of custom. So if the p-value is less than 0.05, then the results are deemed significant, not the product of chance. But there's other things you should look at. In addition to the p-value, the size of the variation or the strength of a relationship can be used to interpret the results. So looking at the variability of your data. So just don't only look at p-values. For example, there's a correlation coefficient. If you remember the data that I gave you with the scatter plot, you can do correlation analysis. And an R value of 0.94 is almost a one-to-one correlation. One-to-one would be a perfect 1 score for an R value. So here your interpretation can be the correlation coefficient of 0.94. It indicates a strong positive correlation. And the probability that R equals 0.94, if there's actually no correlation, is less than 5%. So this is pretty strong. You do have a strong correlation. So here, interpreting the significance of a correlation coefficient, the p-values and correlation analysis are influenced by the number of data points. So hopefully you have a lot of data. Even if the p-value is very, very small, we cannot say it is meaningful in terms of the strength of the correlation. So correlations must be interpreted only using the correlation coefficient. So here it's better to rely on the correlation coefficient. And here's an example. What is a big difference? Like how big is big? So here you're comparing 2 different means. So you can have a very large effect size. This is the ratio of change and distribution. So this effect size is D. You can take in the difference between 2 means, and then that's in the numerator, and then denominator, you have standard deviation pooled. and then you can calculate this effect size. So how big is big? So if the effect size is zero point 0.8, it is large. If it's zero point 0.5, it's moderate, and if it's zero point 0.2 to zero point 0.3, it's considered small. And I'll put a little cartoon there, a little mouse. So effect size, again, is the ratio of change and distribution. And hopefully, when you are comparing the changes, that the changes are bigger than the noise. So changes become more difficult to detect with larger background noise. You probably heard of the signal to noise ratio. I do a lot of electrophysiology work. So noise is always a big factor in my research. So you can consider the noise, the trees. So hopefully, the changes that you're measuring are actually bigger than the noise. So maybe that elephant is big enough to be able to be seen amongst the trees, but maybe the duck and the mouse, these changes are too small, and there's too much background noise, and you cannot detect the differences. So, so how big is big? So hopefully your effect size is large. So sometimes even big changes are hard to detect if the background noise is large. And another analogy for the background noise that could be your variance. The variance can be very, very big, and it makes detecting differences in the means difficult. So, so this is a related concept as the signal to noise ratio. There's a signal, and then there's the noise. Of course, you're collecting these two together on a strip chart recorder or on the computer. And then hopefully you can see the signal come out even though there's a lot of background noise. Okay, another metric I wanted to introduce is the 95% confidence interval. X is the mean, and then you have standard deviation, the square root of it, squared divided by n, which is your sample size. And this represents the lower confidence interval, and then the upper confidence interval is here. So it's everything within 1.96 standard deviations of the mean. And basically, a lot of computers will do this calculation for you, but basically, in a nutshell, this is the range in which 95% of your data will fall. If you perform the same experiment on a given population 100 times, you'll have 95% of your data fall within this range. And this actually comes in with the hypothesis testing, and again relates to the p-values being 0.05. So the effective variation distribution decreases as the sample size increases. This is one reason why it's always good to have a larger sample size. So then the effect of the variation distribution, this effect decreases as the sample size increases. So unfortunately, some studies, when if you're studying like a rare disease, your sample sizes will actually be very, very small. But if you can increase your sample size, it's usually better for statistics testing and parameter estimation. Again, standard error is not the same as standard deviation. So standard error is more factors in with the variances. So here, again, 95% confidence interval. I want you to think about the 95%. And then here's actually a range of standard deviations. And then it was 1.96 or 1.96 standard deviations has the 95% confidence interval. So actually having all your data come in within 2 standard deviations of the mean, that'll have a confidence interval of over 95%. And then within 3 standard deviations of the mean, you can have a confidence interval greater than 99%, which actually is 0.01 as your p-value. And that's actually, you can start detecting some differences between two populations quite easily if you have um, your data falling in within this distribution. So now getting to research questions and statistical analyses. I wanted to talk about parameter estimation versus hypothesis testing. For example, uh, is there a difference in the death rate and rate of falls between a group of elderly people living in a community that undertook a 12-month activity monitoring program using a wearable activity monitoring device, or like a smartwatch, and a control group 5 years after the follow-up? So here, the emphasis is on 95% confidence intervals or effect sizes. If you're asking, is there a difference? So here you want to compare the two populations, and here the 95% confidence interval is important, and the effect size is important. Hopefully, you can be able to see the differences between the two groups. Uh, or if you're just asking, does a difference occur or not? And this is an emphasis on statistical significance using p-values. So one is looking at the parameters, or you can have a hypothesis: is there a statistically significant difference or not? And that one you want to compare the p-values. So here's some statistical procedures relevant to parameter testing. So you have, again, 95% confidence interval, the effect size. Then there's an MCID. This is minimally clinically important difference. I think this is important in the medical fields. That this is it's different than p-values. And then you also have the MDC. This is the minimally detectable change. How small can the difference be? And you can detect these differences. And to help with that, there's statistical power calculation. And there's also a sample size calculation. Some studies you can actually do a pilot study, and you can do a statistical power test. And if you do this small pilot study, you can look at the variability of your data, and then you can use a formula, and you can put your numbers into this formula, and it'll tell you, what is the minimum sample size that you need to actually detect differences. So, and that's called a power test, and then that gives you your sample size calculation. So, a research question formats, and this is important when you're designing experiments. So, first of all, you should have a good idea of the population that you're studying. This is the group being studied. Then, what is happening. Medical sciences. You have an intervention or you have an exposure. Basically, what is done to these groups. Then you have a comparison, your statistical tests, outcomes, your measures, and then the duration of your study is the time. And this has different analogies: PCOT or PACOT, whether it's an intervention or an exposure. And this is easily understood for studies involving interventions, but it's not applicable in the observational studies. So that's one of the major formats in the medical sciences. So here is a PCOT for non-intervention studies. Here's an approach to exposure. How can we compare or stratify the outcome? And here's the research question: does the presence of dementia affect the walking ability 1 year after a stroke? And here you just have presence or absence data of dementia, and you also have walking speed as a measurable variable. Here's another example for a non-intervention study. What is the relationship between cognitive functioning and walking ability 1 year after the stroke? And then you have walking speed, and then an MMSE score, and you can plot those two. So how can we compare and stratify the outcomes? How much does walking ability among stroke victims with dementia decline in 1 year? So that's one way to look at. You have a baseline and then remeasuring 1 year later. So that's one way you can compare, stratify um, two different measurements. So some requirements for a good study objective. This PCOT, this research question like formula, it should logically follow the study objective. P, that's the population, a participant or patient. E is the exposure, or I, intervention. Then you do the comparison, then you have the outcome, and then time. And here's a summary of the results. Here, the study aims to provide a summary estimate of to the extent to which cannabis use, so that's your exposure or intervention, in adolescents, so the teenagers, that's your study population, is associated with the risk of developing subsequent major depression, anxiety, and suicidal behavior. And that's the outcome of the study. So it doesn't mention any time period, and it doesn't compare, but you probably have like a treatment and a control group. So they probably have a second population of adults that don't use cannabis in this study. So uh, here's so here the research question wasn't really clear. It didn't compare two different groups, and it didn't give the time either. So here is when the research question is clear and the study aim is clear. Here, population is elderly people experiencing memory lapses who have received a diagnosis of mild cognitive impairment, so MCI, and they have not been diagnosed with any other condition that lowers cognitive function. And the family, of course, you have informed consent, so that's always important for medical studies. So here's the intervention, remote aerobic exercise program using a tablet ergonometer. 30 minutes a day, 5 times a week for 8 weeks. You have a control group that didn't use this. And then the C, which is actually, the comparison group is the tablet-based memory training. So they're taking a test on the tablet, and the outcome is memory functioning, and then you have time period 8 weeks and 1 year. So this is a much clearer study question. The study aim is clear. The timeline is clear. So here the aim of the present study is to evaluate the preventative effects of 12 months follow-up of a remote aerobic exercise program on memory loss among elderly people diagnosed with MCI, so the mild cognitive impairment, after seeking treatment for forgetfulness compared to memory training alone. So this has a very clear objective and a way to measure it and an intervention program. So, and here's a well-written study objective. So, here, the aim of the present study is to evaluate the preventative effects at 12 months follow-up of a remote exercise program on memory loss among elderly people diagnosed with MCI after seeking treatment for forgetfulness compared to memory training alone. So this actually suggests that statistical tests will be done, and also the results will be in the tables and figures. So here you can have the control group, the memory training, and then the intervention group that they have the aerobic exercise, and then you have the results of their memory function. And then you have the main effect, either the time, um, or the group, the different groups, and then the interaction between time and group. Okay, so real quickly, I'll just talk about research accuracy and precision. Um, and these are important aspects of any research design. You should be thinking about what biases that you may have when you're trying to answer a research question. And bias is another word for error. And so and that relates to accuracy. Um, And you also want to be as precise as you can. So you want to have the highest degree of precision possible. And together, these make up accuracy and precision. So, how can you pose a significant research question? So, here's a bias, here's error versus precision. Here, um, are we largely accurate no matter how many times we throw a dart? And then precision, do the darts land in the same place no matter how we throw? That's the distribution. So high accuracy and low bias is hitting the target all the time. And if you have a lot of sampling points that are around the target, that is also highly precise. That's high precision. Here is an example of high accuracy. If you take a mean, a value, the mean is probably the bullseye, but you're all over the dartboard. So accuracy is high on average, but precision is very, very low. And here, you have very low accuracy, but high precision. So it should be precision is high on average. So these are four different distributions. And here you have high accuracy, but low precision. And of course, any study, you're hoping for high accuracy and high precision. Um, if you have low accuracy and high precision, maybe you didn't calibrate the instrument that you're using to collect the data. There could be some problems, and usually this problem is solved by doing calibrations. So, and this all relates to reliability. So I can talk about accuracy and precision and give you all these pictures of dartboards, but basically, the less bias you have, the the more accurate you are, the quality of the evidence is considered higher. So these are can be different studies like meta-analysis of randomized controlled trials. You can have, and this is the spectrum of how reliable the evidence is. So those are the best studies are the randomized controlled trials. But if you have well-designed comparative studies, these are not randomized. They may have more bias, and then well-designed quasi-experiments are more biased. And then you have well-designed non-experimental descriptive studies. And these are observational studies or case studies. They can have, in general, even more biased. Or if you just have opinions, or these are not scientifically collected data. Some specialist reports may contain the highest amount of biases. So you want to aim for randomized controlled trials, and the meta-analysis is actually looking at several published papers and doing analysis of multiple randomized controlled trials. And they tend to have the smallest bias. So to deal with biased data or errors in your data, of course, these you can never totally get rid of error. You always have to deal with it, and that's why you look at type 1 and type 2 error, and you choose the p-values 0.05. But to minimize the bias, you want to consider randomization. You want to make sure every uh, data point that you collect is independent. Um, I do a lot of ecology studies, and I make sure that my data points, my data are randomized. And I study pheromones of beetles, and I test the pheromones in traps. I put the traps in the forest. I make sure I randomize their position to control for spatial effects. Um, I also change the location of the trap every time I check the traps, and that will, um, you know, also randomizes each data point because you're controlling for timescales as well. So also, you want to have some criteria for non-inclusion for studies. This is more having like human subjects. So you want to screen your patients and you want to have as unbiased data as possible. So you may have some exclusions from your studies. And be wary of measuring some factors that may create biases. There's also analyses of factors that may create biases within various subgroups that you're looking at. So you want to be aware of all these, and these vary from field to field. So in the end, you want to connect your data with your statistics whenever you're reporting your statistics results. Um, you, it's a good idea to know your degrees of freedom. These are uh, important with sample sizes. And when you're establishing a research question, it's important to anticipate which statistics tests will be used. And that's why you do these tests for normality or homoscedasticity of your data. So you can choose the right statistical test based if you have a normal distribution or not. And this will help to reduce the potential effects of chance and bias in your samples. So at this point, I just wanted to share with you some tools and some applications for statistics. And there's a lot of programs that are out there. Um, Probably as an undergraduate at university, you've been introduced to several statistical programs. Also, in just using Microsoft Excel, the data analysis package, which is an add-on in Microsoft Excel. You can add a descriptive statistics package, and you can also do some more advanced statistics even with Excel. So whenever you're publishing your results, it's always great to have some graphics. Like earlier in the presentation, I showed you some histograms that show the distribution and spread of the data. These are always a highlight for any research publication, is having illustrations or schematics or images. And it's important to have data visualization. You should be able to see and understand the distribution of the data, how the data were collected, what statistical tests were used, what are the degrees of freedom in the statistical tests. And here are some programs for artwork and images. There's AutoDraw, these to help draw some shapes and objects, or SciDraw. This helps drawings of scientific objects such as cells or animals. These are uploaded by scientists, and users can download these images and use them for free. There's also Noun Project or BioRender. These are image repositories. If you have a lot of illustrations you want to show in your results section. Then there's Inkscape or Vector for creating drawings, and then Canva for making layouts, and they have some good stock photos as well. This is actually from a Nature article on tips on how to have great graphics, having impactful graphics. And another difference I want everyone to know when you're creating figures that you're planning to publish. A lot of the statistical programs, they'll actually give you, they'll plot the graphics in vector. Vector is basically an object-oriented image, and basically graphs, diagrams, schematics, and cladograms are created in this vector format. And you should submit these as vectors. And they basically, vector images are based on mathematically described points, lines, and areas, and therefore they can be easily resized and edited. Um, uh, you want to avoid using raster, which are bitmap or scanned images. Raster images are basically images made out of pixels. They are not described mathematically. They cannot be edited easily. They cannot be enlarged without losing resolution. So photos, scans, and continuous tone data plots are examples of intrinsically raster images. They're fine to submit, if you wanted to submit pictures. So here's some programs. These are usually vector, like Adobe Illustrator, PowerPoint, um, also CorelDRAW, if you recognize some of the file extensions. Adobe PDFs, and then these EPSs, these can be either vector or raster. And then, of course, the pictures are almost always raster, so including Adobe Photoshop. And this is from actually the Annual Reviews Guide, which I just submitted a paper. And here's an example of why the graphs are much better in a vector form. So if you look, at first glance, they look the same, and the vector format is resolution independent. So if you zoom in on the data points, it's very crisp at all magnifications because all these points are mathematically described, and you can actually edit. You can control the points, and they're connected by lines. They're called paths. And lines, colors, and gradients and type are instantly changeable. So you can edit all of these. So paths can be manipulated where appropriate with handles. Whereas on the raster format, it's just pixels. So if you zoom in, it's resolution dependent. So you have to have a very large file size, and it's difficult, for journals to actually deal with these. So you want to keep your graphics in vector form. So here's a tool for vector graphics, Inkscape. This is a professional quality vector graphics software, and you can render primitive vector shapes and text. You can also create shapes for further manipulations, or you can just use a statistical program for data visualization. And this usually generates those vector graphs. And, uh, and this is great to create visual representations of large data sets. So you have ggplot, GNUplot, matplotlib, RStudio, and I'll explain a little bit more about R, because just as a journal editor, this has become extremely popular. Way to not only analyze your data, but also to graphically show your data and publish your graphics from your statistical tests. And then MATLAB, of course. This is an old one, but good one. And these are great for making graphs from your data and your results of your statistical tests. You can also use Google Charts and also Microsoft Excel as well. So Excel is usually a good start because you're usually entering your data in Excel to begin with before you manipulate your data for these other statistical programs. So here are some statistical and graphing programs. So R is actually a programming language, and I would encourage, if you have a chance, to take a statistics course in R to do so. And I'm going to share with you on the next slide a book that is really like the entry-level, beginner-level book for an introduction into our language programming and how to create really nice graphics for publication. And then there's some other statistical programs. So again, Microsoft Excel, you can do quite a lot of statistics in that program. And then there's Statistica, SAS, which is Statistical Application Systems. This is an expensive one. Individuals cannot get a copy of it. Usually your institute will rent a copy of it, and you can do your statistics on the computers at your school or your university. So that one's hard to get. Actually, that's what I trained on. And then there's SPSS, which is more on Windows, and then Minitab and Apple. So I just wanted to share a nice book from a friend and colleague, Professor Alexei Shiponov, and he's actually a botanist, and he wrote this wonderful book. It was actually written in Russian, but it was translated to English, and the translation is excellent. And here's just a snapshot, um, of data, and it's actually a lot of what we discussed in this webinar, about where data come from, and what data can do, what it cannot do, why do you need data analysis, and then some really basic. You can download R online, and actually the links here. You can actually download R, and it's a shared program. And then he gets into how to launch it and how to actually play with R, and enter R, and he'll give you some sample data sets, and it's very easy to construct some very, very nice graphics that you can use to publish in your next scientific paper. And this is actually the best reference that I've found for beginners. So, some take home messages from this webinar. I wanted to thank everyone for their attention. It's important to choose the right statistical test according to the type and distribution of the data, like those Shapiro-Wilks test and the Levine's test for normal distribution and homoscedasticity. Basically, any parametric statistical test assumes the homogeneity of variances, that the variances are equal between the two populations. But most of the time, they're not. So you have to choose a non-parametric statistical test or do data transformations. I didn't get into data transformations. That's a topic for another statistical lecture. I also want you to understand the raw data and check its distribution visually. This is the data exploration that I discussed earlier. So even if you have decided what statistical test you want to use, it's good to explore your data with descriptive statistics, and then look at its distribution visually. And then you can choose like an aim to which parameters you want to estimate in your study. I gave you some tips on how to make a research question clear. I showed you one research question when it was not clear, and then gave you a couple examples of a clear research question. Number 5, make sure the statistical test that you've chosen follows logically from your statement of the research objective, and you should take appropriate measures to increase your study's accuracy and precision. Usually, the higher the sample size that you have, the smaller effects of variability have on your study. So you can overcome highly variable data with larger sample sizes, and you can even have do a power test on a smaller sample, and figure out what is the minimum sample size I need to detect the differences between two means. And then finally, my take-home message is learn R. It's free. It's really happened in the last 10 years that R has become very, very popularized. And it's not just any one field, it's across like all scientific disciplines. And it's basically community sourced information, and all these R packages that are out there. They're developed by scientists like you and me, and then shared with the general public. So I know we're supposed to have 30 minutes for Q&A period, but we only have about 15 minutes for Q&A. So at this point, I wanted to thank everyone for their attention. I know statistics is not an easy topic, and I hope that this gave you a nice introduction on statistics and why they're important, not only for your studies, but also for communicating it in scientific journals. So thank you for your attention. So at this point, you can type your questions on the right side of the chat, and I'd be happy to take your questions at this time. Okay, well, Vishal Venu asked, "Hi, how do we statistically define the normally distributed data?" So um, basically, your your data is yeah, you're defining your data when by the choice of the statistical tests. If you're choosing ANOVA, like analysis of the variance, uh, that yeah, you're implying that your data were normally distributed. So basically, just the simple choice of your statistical tests help to define whether your data are normally distributed or not. Um, if you don't do these checks, if you just do an ANOVA and you don't do the Levine's test and the Wilk-Shapiro test, the reviewers might ask you to do it, or your thesis committee members might ask you to do that. And if they fail those tests, then they fail the assumptions um, of a normal distribution and homogeneity of variances. And then you have to use non-parametric statistics. So here, that's simply doing those pre-checks on your data sets, and then performing the tests themselves. That'll automatically just classify what kind of data that you have. Like categorical data is most certainly um, non-parametric statistics that you'll need to compare those groups. I'm just scrolling. So so the difference between a t-test and an f-test. Well, the t-test is a basic comparison of two means, and that's actually called the student's t-test. And then the f statistic is actually an analysis of the variance. So the t-test tests the means. The f-test actually will compare the variance between the two groups. Analysis of the variance usually followed, if you have a significant result on your ANOVA analysis of the variance. Usually, there's a post hoc analysis that's done after the ANOVA, and then usually a Tukey's test is compares the different groups. So you may detect a difference between multiple groups, but you don't know which groups they are, and then you do a post hoc test. So again, t-test is usually just only testing means where F statistics is part of a ANOVA test, where you're testing the variances. So yeah, to Haitham Alamad, I asked, what is the difference between the p-value, significance value, and the confidence interval? Um, Basically, the the significance level is your alpha. So alpha is 0.05. The p-value is basically, if the alpha value, your significance value, is at 5%, 0.05, then when your p-value is below 0.05, then you can reject the null hypothesis and say that there is a difference in your data. So, basically, the significance level, that's your choice. You can choose, and it's alpha equals 0.05. And that basically says if the p-value is below 0.05, then we can say there's a significant result. And then the confidence interval, that looks more at the bell-shaped curve on your data distribution. So a 95% confidence interval, basically uh, it covers the distribution of your data, and that's the probability of the data point you collect falling within that 95% range. And that's also related to the p-value. So only these extreme values fall outside that range. So the 95% confidence interval is very inclusive. Then there's standard errors. Standard errors are different, and these are calculated in different ways. But yeah, those are actually all related. So, okay, so there's a question on a power test. This is from Rana Aldiwala. Hi, if I did a power calculation for my study and it was 187, but I only got 145 because it is a questionnaire, and that's the only responses I got. Can I go ahead and analyze it? So, um, so if you fall short of what is the minimum sample size, I would go ahead and analyze it anyways. But in the discussion section, you can you're right that you came close to the sample size that was suggested by the power test, but just due to a lower sample size, I was not able to do that. You would treat the results with slightly more caution. And as long as you put those caveats in your discussion, usually reviewers will, um, they might not be happy about it, but they would actually understand, the limitations of your study. And of course, there's always limitations with any study. So they wouldn't be as reliable as if you had the bigger sample size, but they're not totally worthless. But those will just be discussion points for your study. So you elaborate on ad hoc analysis. Basically, a lot of these statistical analyses, so using the plural, uh, like um, like ANOVA, which is a pretty standard one-way or two-way ANOVAs. Um, yeah, ANOVAs compare often more than two groups. Where you have a t-test will compare two different groups. ANOVA can actually compare multiple groups, and you'll get a significant result. You get a p-value of less than 0.05, but you don't know where the actual differences are. What two groups are different? And in order to answer that question, you have to do these ad hoc or post hoc tests. Um, and I gave the example of a Tukey's test, and there's other tests. There's like least squared differences, which is more conservative. There's a lot of tests you can choose from, and basically they help identify between which two groups the statistical difference occurred, and um, you can adjust the p values in some cases, where maybe you're because if if you have a if you have 10 different groups and you want to do a t-test on each of these 10 groups, it actually lowers, you can't compare, 10, it reduces the p-values actually, by a factor of 10. That's why you want to do an ANOVA, because it'll compare all the groups at the same time, and then a post hoc test will actually detect which of the two groups actually had the difference. So you have to be careful when you're doing multiple comparisons. It's better to do the ANOVA over the t-test. And actually, if you have an idea, if one group, let's say you're testing a cholesterol drug, and this goes to the next question about having a one-tailed or a two-tailed test. Um, if you're testing like I forget the name of the drug, like Lipitor, or one of these like these cholesterol lowering drugs, and you want to compare a control versus a treatment group. You're going in to the study knowing, oh, maybe the treatment group has lower cholesterol, and here you can do a one-tailed test when you have an idea of a direction of an effect that you're measuring. Uh, Whereas if you're doing another experimental drug, you have no idea, like let's say red blood cell count, you have no idea if it's going to be higher or lower. Then you want to do a two-tailed test rather than a one-tailed test. So that's an example I can just think of off the top of my head. So I think we ran out of questions. So at this point, there's a form that I think my colleagues will post, and this is a feedback form. You can click on it and give us your feedback, because of course we would love to have some more webinars on important topics, and this will help us to design our next webinar for you. And finally, there's a PDF book on our statistics that I hope that was shared with you, either with a link or with a file. So I just got a note saying we have some more questions. So I just scrolled in the chat. So oh yeah, there's some more questions here. Okay, I think I answered the question about the normally distributed data. You know, like yes, you can plot them in histograms, but it's better to do these Shapiro-Wilks tests, and I think the cutoff value is 0.05, and yeah, actually, I think you want to have the value below 0.05, because you want to, because I think the null hypothesis is that the data are not normal. So, and then you get a 0.05 or below, and then reject it, and you say the data are normal. That's what I think from the Levine's test and the Wilks-Shapiro test that I did on my dissertation work. It just works like any other standard test, 0.05 being the cutoff level. And you can determine if your data are normally distributed, and then if the variances are homogeneous or not. So, okay, another question from Rim Sagiri. Usually as pathologists, we set abnormal ranges as median or mean, plus or minus 2 standard deviations. That actually takes into account slightly higher than 95% confidence intervals. And this can be relevant for variables with normal distribution. However, sometimes, how do we deal with variables with no normal distribution? How do we set normal or abnormal R? So what is R? Okay. Talking about the correlations. So yeah, I think you get into nonlinear regression, which I think that's a dealing with non-normal like scatter plots. Is very, very advanced statistics, multiple regression analysis, or nonlinear regression analysis. Okay, I think we only have about 1 minute left. I'm scrolling around. Actually, one person asked about the statistical programs to use. So, which is better for data analysis, R or SPSS? Well, I think we're looking at apples and apples here. There's uh, no one statistical program is better than the next one. Um, they're all based on published statistical tests that are well known in the literature. It's just different programming. You may find it easier to do graphical representations of your data in R, or maybe it's easier to do the statistical tests in SPSS. So you may get the statistical results, and maybe one program is easier to use than the other, and then choose the best one for graphics. So I'd say they're both good. It just depends on what you're most comfortable with. So, all right. Well, I think that's about it. So we're going to wrap up the webinar. Thank you very much. I'm so happy to see all these questions, and I'm glad that we had time to answer most of them. And I wish everyone the best of luck, and thank you for tuning in. at the end of your workday. I know Saudi Arabia is the same time zone as Moscow. So again, thank you very much, and I hope to see you at a future webinar.